este segundo día vamos a comenzar con una sesión sobre soluciones tecnológicas. Así pues, damos paso a Andrea Marcelli, de Hispasec, y a Luca Cetro. Andrea Marcelli es investigador de seguridad en Hispasec, se graduó en Ingeniería Informática en Turín y está trabajando actualmente en el proyecto Q2. Sus intereses de investigación incluyen, entre otros, el análisis de malware y el machine learning. Luca Cetro es investigador de ciberseguridad, se graduó en Ingeniería Informática y sus estudios se centran principalmente en la ingeniería del software, machine learning y la inteligencia artificial. Pero también es un apasionado de otros temas que van desde la criptografía hasta el análisis de malware. Ahora sí os dejo con su ponencia que lleva por título Looking for the Perfect Signature, an Automatic YARA Rules Generation Algorithm in the L Era. Que la disfruten.
Well, good morning. Thanks a lot for having us here. It's a great pleasure to be here with all of you. And today the talk is titled Looking for the Perfect Signature, an Automatic Rule Generation Algorithm in the AI Era. My name is Andrea Marcelli. I'm a PhD candidate at Politecnico di Torino in Italy. And currently I'm a security researcher at Hispasec Sistemas, which is a Spain-based security company. And today with me there is Luca. Please, Luca.
Well, that's been said pretty much everything about me. I just graduated from the Master of Science in Computer Engineering at the Politecnico di Torino, and I'm currently working as an independent security researcher on this project.
Okay, today we'll talk about the problem of automatically generating a malware signature. Then we will go through the framework that we developed to solve this problem and the tool that we developed, which is called YAGEN-PE. And then we will run shortly with results and the demo, and we'll conclude the talk. So let's start talking, what is a malware signature? So the malware signature is a unique pattern that identifies the malicious code. And the problem with malware signature is that as malware evolves, new signatures need to be generated frequently, which is a huge effort from the employee perspective. So automatically generating a signature is really needed. And today there are mainly two types of signatures. There are syntactic ones and semantic ones. Syntactic signatures are those based on strings, X sequences, regular expressions. That is everything that you can extract from static analysis. And this is where most of the research brought from academia and industry focus on. On the other hand, we have semantic signatures, which are different because they try to provide an abstraction of the malware behavior. And today we'll talk about Windows executable, so creating malware signature for Windows executable for YARA, but the entire approach is generic and can be applied to other platforms too. And this is not just another machine learning classifier, it's much more, and we will go through all the details. When we talk about malware signatures, we have to talk about YARA. YARA has been defined by its creator, Victor, as YARA is to files what snort is to network traffic. And it was designed to be extremely fast, and currently is the de facto standard way of creating malware signatures. And the most interesting thing is that it natively supports syntactic signatures, but semantic signatures can be created in YARA too through custom modules. For example, PE modules, cuckoo modules, and so on and so forth. This is an example of YARA rule. The most important section is the condition section. This is where the logic of the rule is placed, and also where all the semantic attributes are written. In this case, we can see some attributes from the PE header of the file. Let's talk about work motivation. So why we did this work? First of all, we want to create an approach that works with more than 1,000 files in input, so something that is scalable. Then we want to create something that is fast, because it's a very important requirement in the industry, and we had the goal creating a rule for 100 files in about 5 minutes. Then we wanted to achieve limited false positives. That is, we want to avoid unwanted detections. And we want also to increase the number of true positives. That is, detect new malware families, new malware variants. So the framework that we created is a pipeline that in input has the PE files, that is the Windows executable files, and in output it outputs the YARA rules, a set of YARA rules that covers all the files in input. There are three main sections, three main stages. The first one is the feature extraction. That is, for each file input, some features are extracted. Then the clustering is applied. The clustering is used to make everything scalable. Although it's an optional step, it can be skipped in case. And finally, we have the signature generation, which is the actual algorithm that generates the signature. One key point is that the input is generic. That is, we are talking about Windows, but it can be anything. It can be anything, but of course, the goodness of the results is somehow dependent from the input. So the rules in output are more effective if the files in input share something in common, share some traits in common. So in output, we have a set of YARA rules that will cover all the files in input, always. But the number of YARA rules that we have in output depends from how similar are the files in input. So the first stage of the framework is the feature extraction. In the feature extraction, each file is analyzed and some features are extracted from this file. We mainly rely on static analysis and existing YARA rules. Static analysis extracts some features from the PE header. So we use the PE file module from Python to extract those features, and each feature can be easily represented as a block in that gray grid that you can see in the slides. So each block is a feature, and it can be something extracted statically or something that that derives from a YARA rule matches. So we have a set of YARA rules available. For example, we have thousands of rules available on GitHub freely. We can use them to extract some expert knowledge to be added to the new rule generation. So another key point is that features are generic, and we don't really care about what a feature is. Because in the end, YAGen, our tool, is just an algorithm that provides an approximate solution to a hard-to-solve optimization problem. So we don't really care about what a feature is, and we can use anything as a feature as far as it can be translated into a valid YARA rule. Currently, we don't use strings, binary patterns, regular expression, although we can add them. Sorry, we don't use strings, binary patterns, or regular expression, but we can add them in the future. The second step is the clustering. Clustering is what makes everything scalable. So clustering is a machine learning algorithm, a type of machine learning algorithm that finds similarities among the input. In our case, we have files in input, so through the clustering, we can find similar group of files. We use mainly two approaches. We devised two approaches. One is based on a density-based algorithm. The other based on a unsupervised decision tree. And the key point is that from each cluster that we found through the clustering phase, we generate a new YARA rule. So the density-based approach is based on HDB scan, which is the state-of-the-art of density clustering, density-based clustering. We use this approach because real data has outliers, and moreover, the density-based clustering scales well, very well. We use the Jacquard distance to compute the distances, and we tend to have clusters which are very small. But it's much more interesting the other approach, which is the unsupervised decision tree. In this approach, each cluster is split using a feature. So we start from one group, and then we split that group in two subgroups, thanks to the value of a feature. And the feature that is chosen is the one that maximizes the distance between the centroids of the clusters, of the new clusters. We approximate the calculation of the centroids so that everything is faster and more scalable. And for this reason, we also use the Russell-Rao and Jacquard distance. And all the process continues until we hit a stopping conditions, which is experimentally set as a minimum threshold of the distance between the centroids. So here you can see an example of how the clustering proceeds. We start from one cluster, then we choose one feature, which is the PE import, the first one that you can see. So we found our two new clusters, other two new clusters, and the entire process is repeated until we end in the last row with some clusters, and for each of them, we have to generate a rule in the next step. But the real advantage of this solution is that actually computing the cluster, we are also creating a part of the rule, also in this stage. Because each features that is chosen to split the clusters is also something that can be translated into a logic rule and then into a Yara rule, as you can see in this example. So there are clusters that have that feature, are clusters that do not have that features, and the combination of this information is actually a rule. Then for each cluster, we have to generate a signature. And the idea of signature generation is very simple. We start from two samples. Those two samples have some features. Some of them are of the same type. And we can just use their combination as a signatures. So in this example, the combination of yellow and green features is a signatures. The problem is that in the reality, everything is much more complex, because it's very difficult to find just a unique pattern to cover all the files in input. And the solution is to find the optimal combination of attributes that allows to cover the entire file in input, the entire input. But luckily, this problem can be reduced to a variant of a very well-known problem, which is the set covering problem, which unluckily is NP complete, so it's very difficult to solve. But in our case, we just need an approximate solution, so we created a dynamic greedy algorithm to build the signature. Mathematically speaking, building a signatures can be represented into this form, which is a normal form. In particular, is the disjunctive normal form, where the final signature is a combination, is the disjunction of clauses, and each clause is the conjunction of literals, where each literal is a feature that we extracted in the first phase. Representing the solution with this form is essential because it allows to evaluate how effective is the result. Because creating a signature is very simple. Evaluate how effective it is much more difficult. And currently we use as a weight of a signature simply the number of features in each clause. So we count the number of literals in each clause. So in order to evaluate how effective is a signatures, we devise a system, very simple system, based on two thresholds, Tmin and Tmax, and we say that the optimal signature is the one that has a weight between those two thresholds. And because if a signature is below Tmin, that is too generic, it will produce a lot of false positive, because it has just few characteristics that matches a lot of files. On the other hand, if we have a signature with a lot of features, which has a weight which is above Tmax, it means it will match just few files, just few input files, because it's too specific. So the goal of the algorithm, and this is what the algorithm actually implements, is to create a signatures, a combination of literals that has a weight between the two thresholds. So this is what we implemented into a tool which is called YayaGenPE, yet another Yara rule generator for PE file. And this is what Luca will present to you now.
Thanks, Andrea. So a brief recap of YayaGenPE and what it consists. Actually, YayaGenPE consists of the two clustering algorithms, which are HDBScan and UDT. and the two algorithms for the rule generation, which actually solve the set covering problem that Andrea just explained. The current version of AIGMPE also implements its own Yara rule parser internally, which is used for the feature extraction and actually to compile the rules that are tested against each of the malicious samples for which we want to train the rules. The current version of the framework is written in Python 3 and consists approximately of 2,000 lines of code. Now, if you're interested, at the bottom of this slide, you find the repository of YayaGen, which is the framework that targets the Android malwares. Now, in this part of the presentation, we will talk about experimental results. Specifically, during this work, we focused on the most relevant questions for what concerned the malware detection, such as the true positives coverage, the false positive resistance, the dataset coverage, and the debugging resistance. In this slide, you can see on a high-level overview of the comparison of AIGMPE against the today's state-of-the-art signature generation algorithms, in which the three leftmost columns represent Yara rule generation frameworks, while the one in the middle, which is BES, targets the CLAMAV signatures. Now, as Andrea just explained, AIGMPE is based on a set of PE header fields plus some Yara rules, which is kind of different from what is offered by the other signature generation frameworks, which are mainly based on strings or binary opcodes. Binary opcodes actually are instructions of some functions. Moreover, AIGMPE actually produces rules by solving the set covering problem, while most of the other tools rely on a whitelist of strings or whitelist of functions, which, by the way, have to be kept constantly updated. Now, if you take a look at the fourth row, you can see what I was saying before about dataset coverage. That is, AIGMPE actually was, in our work, the only tool that supported completely the training set coverage, in that the other Yara rule generation frameworks were not capable in some occasions to provide the rules that cover the entire input training set. Now, in the next 3 slides, we will address 3 families that we had in our dataset, and we will focus mainly on the number of false positives found and true positives found. The first family we will take into account is the CryptoWolf family. And by the way, here we will compare AIGMPE against YARGEN and Yabin, which have been proved to be the best Yara rule generation frameworks among the 3 reported before. As you can see here, AIGMPE is the only tool to provide no false positives in all the training conditions, while at the same time providing a number of true positives, which is actually comparable with YARGEN and Yabin when they do both produce no false positives as well. Now let's move to the server family. The server family consisted in 550 samples in our dataset, and as you can see here, AIGMPE produced less false positives than the other signature generation frameworks in most occasions, while at the same time providing a higher number of true positives. On top of that, if you compare AIGMPE, the third row, which does not produce false positives, with Yabin, the first entry, which did not produce any false positives, you can see that AIGMPE true positives are higher. This is the last family we had in our training dataset, which actually is the Tesla Grid family, the biggest one. It consisted approximately of 2,500 samples. And here, as before, AIGMPE did not produce any false positives in any of the training conditions we tested, while at the same time providing a number of true positives, which is comparable and in most cases also higher with respect to the other signature generation frameworks when they do produce 0 false positives as well. In this slide, we will take a look at the absolute evaluation of the AIGMPE rules, in that those rules are tested against the VirusTotal RetroHunt platform. Specifically, this platform tests the user-provided Yara rules against a corpus of 100 terabytes of data, which actually consists approximately of thousands of millions of malicious samples. Yeah, samples, not necessarily malicious. So we trained the rules using the families in the leftmost column you see in this table, and using the algorithm that you see in the column next to it. And as you can see, the total number of matches found is rather restricted, with a high true positive ratio and a lower restricted number of false positives. This actually tells us that rules produced by AIGMP are likely targeted towards the malicious family they were trained on. We actually also manually verified that by making sure that most of the true positives found were actually belonging to the same training family that trained the rules that were being tested. In this last result slide, we will take into account packing. Specifically, we wanted to understand whether AIGMP rules were capable of being packing resistant. So in order to do that, we rely on the most common open source packer, which is UPX. And we selected actually the families in our dataset that were proved having some malicious samples packed with UPX. And we trained those families on the algorithm that you find in each row of this table. We furtherly tested the produced rules against a dataset of approximately 3,000 UPX packet goodwares. And in each entry of this table, you can see the number of false positives found by the AIGMP rules. Now, as you can see, it is pretty safe to say that the AIGMP rules were packing resistant, at least for what concerns UPX. We conclude this part of the presentation with some signature statistics. Specifically, here you find 3 families of malicious samples of increasing size. And at the rightmost column, you can find the time implied to train those families. Now, let's take a look at the number of rules. Specifically here, we have determined during our studies that approximately both the UDT and the HDB scan clustering algorithm produce 1 cluster each 5 applications, but HDB scan tends to produce 20% of outliers, which is the reason why, if you notice, the number of rules produced by the HDB scan are usually higher than the number of rules produced by UDT. So let's take a look at 2 demos. So the first one is the simplest one. In this case, we are giving to AIGMP only the directory of malicious samples to be targeted, and we are specifying the algorithm to be used. In this case, the family was small, so we did not need any clustering. Now, as you can see, the process is pretty fast. To produce a rule on 6 samples, it took just a second. And here you will see the rule, which actually consists of quite a high number of literals that are all shared among the several samples that we had in the training set. Now, let's move to the second example. Actually, this is use the same directory of malicious samples to be covered, but in this case, we will also provide a directory of VRR rules. These rules were actually targeting some packing opcodes that we found through PID, which is a common database of packers. And as you can see here, now the framework is scanning the error rules, simplifying them, and parsing them. Once they are all parsed, they will be compiled and tested, which is actually appearing now, against all the malicious samples in the directory that we provided as input. Now, the process of creating these rules might take some time. This is why we also included an internal database to store the rules that have already been parsed and simplified, so that you don't have to do that again if you provide the same directory. Now, as you can see here, there is a set of private rules, which are the malicious sample rules that were matching, that we actually provided as the second parameter, which is the directory of VRR rules. These rules are private in that they will not trigger a true positive in case the entire rule, that is the one that you are seeing now, will not match in its entirety. As you can see here, there is quite a high number of literals, which is mixed, by the way, with some names of the private rules introduced in the top of the rule. And this is something that we will talk about in a few seconds. Okay, so let's talk about the limitations so that I can connect back to what I was saying just a few seconds ago. The first limitation is the fact that actually Python PE file is not completely compatible with the ERA PE module. This means that actually not all the features that were supported by the ERA PE module are actually usable by IAGMP as of now. Moreover, as Andrea just said, the rule evaluation is oversimplified in that it consists of the number of features included inside each ERA rule, and this, by the way, might lead to rules that can be overspecific. That is, there might be too many features, which was actually what I was saying before. However, most of the rules that we have tested did not provide problems with a high number of literals, but there might be issues if there were actually really too many. So in order to solve both these problems, there is an optimization procedure. Actually, this optimization procedure is already implemented in the IAGM framework, which consists already of two basic optimizers. Specifically, however, to introduce them, we need to understand which is the better combination of attributes in order to create the best rules. And this, by the way, will modify the weights associated to each of the features of the malicious samples, which will solve the problem of optimization of rules, which means rules might be still targeted but less specific, consisting of less number of features, and of the problem of the importance of a rule and the scoring of a rule. So in conclusion, during this work, we did a survey of the automatic signature generation problem. This work was actually justified by the interest from the research community, and we developed the IAGMP in order to improve the existing approaches. So we thank you for your attention. We thank the organization for this event. It's been a pleasure to be here. And if you got any question, we are here to answer.
Thank you so much, Luca
Muchas gracias.
and Andrea, for your presentation. Antes de nada, disculpen porque llevamos 15 minutos de retraso. We have some questions for you. Okay, only one. Tenemos una pregunta de Agustín que dice, working on some rule set or algorithm to automatize threshold calibration. ¿Están actualmente trabajando en alguna normativa de reglas para automatizar umbrales?
We have some algorithms to optimize the two thresholds. So you can find them in the GitHub repository of IAGN, the Android version, which is online. And we will probably soon release also the Windows version, so you can find them. But briefly speaking, there are tons of optimization algorithms that can be used, starting from greedy algorithms, which are the most simple, to some hill climbing algorithm, or something more complex like a genetic algorithm or others. So there is an entire set of optimization algorithms that can be used. It all depends on how much time you have to find the best solution.
Okay, thank you so much.
Thank you.
Thank you.